go over question 1. Show that 5 multiplications are sufficient to compute the square of a 2 times 2 matrix. Sure, so if we represent the 2 times 2 matrix as A is equal to A, B, C, D, and let's just write out what we can write out. This gives us A, B, C, D times A, B, C, D, which is some math. Okay, and then in group terms like this term, AC, oh yeah, this is AC. So group this, A plus D, BC plus D squared. So then the 5 multiplications are A squared, BC, this, this, and this. So in total we have 5 multiplications. Okay, 2. What's wrong with the following algorithm for computing the square of an n times n matrix? Use a divide and conquer approach as in Strasson's algorithm, except that instead of using 7 subproblems of size n over 2, we get 5 subproblems of size n over 2, thanks to part A. Blah, blah, blah. Algorithm runs in that time. Okay, so first let's recap what Strasson's algorithm is, and this is directly from the textbook, chapter 2. So Strasson's algorithm is a way to multiply 2 n times size n times n matrices in a time that is faster than O of n cubed. So the idea is to use divide and conquer, and so Strasson. So divide and conquer is like if you have an n times n matrix, you break it up like this, and then this is like classic divide and conquer, not really Strasson's. This is Strasson's. So somehow he realized that you could write the matrices, the entries like this. And if you do so, then you would only need 7 matrix multiplications of size n over 2, where these multiplications are subproblems of the original problem. And then, yeah, so the total runtime, if you use Strasson's algorithm, would take only that. So that's pretty clever. The only thing, or the thing to notice is that the subproblems that are size n over 2 actually are subproblems, i.e. the original problem was 2 matrix one matrix multiplication, and the subproblems are also matrix multiplications, just of a smaller size. Now if we go back to this question. So, okay, so if we're computing the square of an n times n matrix, so let's say we're computing the square of x, and we divide it up into A, B, C, D. And then x squared is A squared. Okay, I'm not going to calculate it like that. Let me just write this guy out here. A, B, C, D. Okay, so then we have plus BC, AC, CD. something like this. Okay, and then so the original problem. So say this is size n, size n, and so we will represent it in this notation as t of n. So yeah, so this sentence is saying that we would now get 5 subproblems of size n over 2. So notice that these matrices are all size n over 2. The problem, however, is that the subproblems aren't actually, or the size n over 2 things aren't all subproblems. For instance, BC isn't matrix squaring. It's matrix multiplication squaring. So you can't say that it's 5 t over n, t n over 2 plus n squared. This is not true because because not sub problems. And I guess one thing that you might ask about is, what if the original matrix, so we know that X is size n times n. You might ask, what if like n isn't a perfect, well, if n isn't a power of 2, then you can't really do this, right? Because like this, we're breaking it up, assuming that you can divide n by 2. Well, the answer to that would be just to pad it by zeros. So if e.g. if x was like x was like 3 times 3, you could just have a 3 times 3 matrix, and then you add some zeros. And then you can do the divide and conquer. And the runtime will be asymptotically the same because the extra zeros, the padding doesn't affect the overall asymptotic runtime. Okay. Part C, in fact, squaring matrices is no easier than multiplying them. Show that if n times n matrices can be squared and theta n to the c time, then any n times n matrices, any matrix can be multiplied in theta n to the c time. Should have corrected that grammar mistake. Okay, anyways. So let's use the hint. So given matrices x, y, is there some matrix A such that we can easily compute x, y given A squared? Cool, so we have A squared, and we want to use A squared to get x, y. So what if I just set A is equal to x? So okay, say x, A is like a, okay, let's say I have something like this. And then this would be like R 2n times 2n, assuming the zeros are a size n. And then if we do A squared, we get x squared, and then it's xy, 0, 0. Okay. So if we set A to this, then we can just take out this entry to get xy. So let's look at the runtime of computing A squared. So it's saying that if an n times n matrix can be squared in that time, so i.e. A squared is squared in, well, A is squared in 2n to the c time. And that is equal to 2 to the c n to the c time. And asymptotically, that is big theta into the c. Therefore, A squared takes this time to compute. And so xy just takes the same amount of time to compute. Cool.
Welcome to discussion 2. Let's go over problem number 2. This is on complex numbers. So remember that a complex number is any number that we can write in the rectangular form, that is at the form a plus bi, where the bi is the imaginary component. And I is defined as the square root of minus 1, such that I squared equals minus 1. We also have Euler's formula that relates the polar form to the rectangular form. And in the polar form, we have the distance of the complex number from the origin, and we have the angle of that number from the origin, namely r and theta. So we have some geometric identities here that might be useful for simplification that I'll highlight for you to see. Okay, so let's go ahead and attempt the very first question. So we have two complex numbers that are 2/10 roots of unity, and we want to compute the product of x and y. And we also want to see what happens when we change those numbers, and we want to know if the result is a 10th root of unity. So let's go ahead and multiply x and y. Note that if you multiply two exponents, the exponents add up. So the product of x and y would be which is a 10th root of unity. This also simplifies to 2 to the pi, or e to the 2 pi I and 4/5, which is a 5th root of unity. So now when we have different values for x and y, let's see what the product of x and y becomes. It's going to be e to the 2 pi I 13/10, which would simplify to e to the 2 pi I 10/10, and e to the 2 pi I 3/10. This would simplify to unity, and we would be left with e to the 2 pi I 3/10, which is a 10th root of unity. Note that whenever our numerator is greater than the denominator, we can simply wrap around, as we've done here. Awesome. So moving along, let's go to subpart B. We have to show that for any nth root of unity, such that omega is not equal to 1, the summation of all powers of omega from 0 to n minus 1 is equal to 0. And this is for n greater than 1. So we have a hint given to us, that is, we can use the formula for the sum of a geometric series as given here. So let's see if we can simplify this. So the key thing here to note is that the summation is going all the way from 0 to n. And in our right-hand side, in the numerator, the exponent is n plus 1. So let's see if we can use that to our advantage here. So let's write this out as omega as a summation k equals 0 to n minus 1 of omega to the k. This is going to be equal to omega to the n minus 1 over omega minus 1. And that is because we have an n minus 1 here. So the exponent in the numerator is an n. And since omega is the nth root of unity, this means that omega to the n is equal to 1. So here we have that this is equal to 1 minus 1 over omega minus 1, which is equal to 0. for this, so moving on to subpart C, we have to find all omega such that omega squared is equal to -1. So the way we can do this is actually by squaring both sides. And we get the equation omega to the fourth is equal to 1. So now let's think about the 4 roots of unity. So this would imply that the 4 roots of unity are e to the 2 pi I 0 over 4, e to the 2 pi I 1 over 4, e to the 2 pi I 2 over 4, and e to the 2 pi I 3 over 4. And these correspond to the 4 roots of unity. So these roots of unity are, so this is 1, this is I, this is a -1, and that's a -I. And clearly from here, the two values that when squared become -1 are I and -I. So similarly for this question, we can square both sides to get an equation of the form omega to the 8 is equal to 1, and we can list our 8 roots of unity. So that's e to the 2 pi I 0 over 8 all the way to e to the 2 pi I 7 over 8. And we want the 8 roots of unity that are not the 4th roots of unity. And these are going to be all the odd numbers. So that is e to the 2 pi I 1 over 8, e to the 2 pi I 3 over 8, e to the 2 pi I 5 over 8, and e to the 2 pi I 7 over 8. And in fact, if you raise these omegas or these roots to the 4th power, you will see that they equal -1. And that concludes the walkthrough of part 2.
All right, hello. So question 3 is a intro question to FFT. So let's go through it. Part A, if the polynomial consists just of one term, the constant term, what is the FFT of it? So we just evaluated at the first root of unity, but doesn't really matter since there's just only one constant, which means that the answer, the answer is P of 0. All right, or actually it's an array that contains P of 0. Now for question B, use FFT to compute these two. So let's just focus on one first. What is this? This polynomial is essentially 1 plus 4x. And we're trying to compute it at the second root of unity. What is the second root of unity? Well, from definition, it's -1. All right. And there are some other useful terms we need to know from the FFT algorithm, which is we have of 2 of 0. We know that that is equal to 1, of 2 of 1, and that's equal to -1. And then we also have the square of each term. So of 2 of 0 squared is equal to 1, and of 2 squared is equal to 1 as well. All right. Now for FFT, we split these two components into even and odd terms, right? So, and then we call FFT on each of the terms. So essentially, we have even terms. E prime is equal to FFT of 1 at half of the root of unity, right? So now that's 1. Okay, we know from part A this is essentially just the term. So there's 1. And odd is then the other one, so P of 1 is odd. So that's equal to 4. All right. There's something to keep note of is we're evaluating them at this. That's where we're evaluating them at. All right. So this is essentially E evaluated at 1. And this is odd evaluated at 1. All right. So now we want to actually calculate the FFT. So we know that P of 2 of 0 to be evaluated at all the second root of unity. So we have P of, we have O of 2 to the power of 0, which is equal to P of 1. Okay, what's this equal to? Well, from definition up here, this is equal to P E of 1 plus, okay, 1 times O of 1. Okay, so from up here, we know that this is equal to 1 plus 4 is equal to 5. And we also have the other term. So P of 1, P of negative 1 is equal to E of 1 because we are using the squared term instead. Oh, sorry, this should be 1. And then plus negative 1 times O of 1. And since we already calculated this again, we can just do 1 minus 4, which is equal to negative 3. So therefore, we know that FFT of 1 and 4 and 2, and that is equal to 5 and negative 3. All right, and using the exact same procedure, we can calculate this. So same procedure, we can calculate that FFT of 3 of 2 is equal to essentially 3 plus 2 is equal to 5, and 3 minus 2 is equal to 1. All right, questions part C uses the answer through part B. So we have this polynomial, so P, this is P0, P1, P2, P3. Okay. The fourth degree unity, so this is equal to I, and it's useful to just write out all the exponents as well. So omega of, actually, let's write this over here. So omega 4 of 0 is equal to 1. Omega 4 of 1 is equal to I. Omega 4 2 is equal to negative 1. Omega 4 of 3 is equal to negative I. All right. Now, we have to split it into its even and odd counterparts. So, the even parts is essentially E of I and E of negative I, right? Because we take the square of each of these, so we have 1 squared is equal to 1, and then I squared is equal to negative 1. And similarly, negative 1 squared is equal to 1, negative I squared is equal to negative 1. All right, and this is just the FFT of, what's the even parts? Well, there's 1, 4, half of this, which is equal to 2. Okay, well, that's just the answer here. So, this is equal to 5, negative 3. Similarly, for the odd counterparts, is the FFT of the odd terms, coefficients, I mean, 3 and 2, 2. All right, and similarly is up here as well. So this is going to be 5 and 1. All right, now we want to calculate FFT, so evaluate the polynomial at all of these terms. So we have P of 1, P of I, P of negative 1, and P of negative I. Using the definition of FFT, we know that this is E of 1 squared, which is 1, plus 1 times O of 1. This one is E of I squared, which is negative 1, plus I times O of the same thing. Okay, now we have E of negative 1 squared, so it's 1, plus negative 1 times O of 1. and e of negative I squared, which is negative 1, plus negative I times O of negative 1. So essentially we just plug and chug. And so e of 1 up here is 5, plus O of 1 is also 5, so this is just plus 5 is 10. E of negative 1 is negative 3, plus I times O of negative 1 is 1. So yeah, this is just actually plus 3 plus 1. This is equal to e of 1, so this is 5, plus negative 1 this time, times 5. This time is 0, and this is negative 3, plus negative I times O of negative 1, which is 1, which is equal to negative 3 minus I, which means that the answer to this question, this answer is 10, negative 3 plus I, this is a plus 0, negative 3 minus I. Alright, part D. Describe how to multiply two polynomials p and q in coefficient form of degree at most d. So the idea is we convert the polynomial from coefficient form to value form. So we evaluate it at some number of points, multiply the points, and then convert back. How many points do we need? Well, we know that p times q has at most degree of 2d, since each of them has degree d. So we know how to evaluate points, evaluate polynomial at some number of points by using FFT, but we have to choose a sufficient power of 2. So what do? We choose 2k to be smallest power of 2 larger than 2d. All right, because in the end, we have to convert back, and yeah. Okay, knowing that, we can now let m is equal to calling FFT, so evaluating p on the 2 to the power of k points, element multiply with FFT of q, which then computes p times q at 2k points. Okay, then take the I FFT of m and 2k to get the coefficient form of p times q. Question 4. This is again practice with FFT, but this time you can use the matrices. So let's do this part. What's the appropriate value of omega? Well, we have 1, 0, 0, 0, right? So that means we can use the next power of 2, which is 4, right? Since this is a degree 3 polynomial, essentially. So we use omega 4 is equal to I. Okay. So now we take the FFT of this, like 1, 0, 0, 0, 4. Okay. What can we do? Well, we can draw the matrix. So the matrix looks like this. Okay, 1. And then we take I, and then negative 1, negative I, negative 1, I, negative 1, 1, negative I, negative 1, I. How do I get this matrix? It's essentially just using the definition right up here, just this definition. I recommend writing this in your cheat sheet for exams. All right, and then we can multiply it by the coefficients. And doing the matrix multiplication, we simply see that this is just 1, 1, 1, 1. Okay. Now, we want essentially to find the inverse FFT of 1, 0, 0, 0. So essentially it's asking FFT of what, using 4, is equal to, well actually, yeah, is equal to 1, 0, 0, 0. Okay. And we just do the inverse FFT. So this question mark is equal to 1 over 4. Okay. Another matrix again. Which matrix do we use now? We're using this one. Okay. So this is simply just 1, 1, 1, 1, 1, 1, 1. Okay, because that's always like that. And then we have negative I over here, and then negative 1 I. This is going to be negative 1, negative I, 1, negative 1, negative 1 I, multiplied by this to get just a bunch of 1/4. Okay. So yeah, that's simply it. If you know what this is and you have the formula, you can simply just plug in the formula and get the answer.